August 14, 2007, 6:05 p.m., Minneapolis. Rush hour traffic. The I-35W bridge over the Mississippi River is packed. Hundreds of cars, trucks, commuters heading home. Then, without warning, the center span collapses. The entire bridge drops 108 feet into the river. 13 people die, 145 injured. And investigators would spend months figuring out how a bridge that had stood for 40 years suddenly failed in seconds. The answer: a single design decision, made decades earlier, to save money, to simplify construction, a decision that seemed minor at the time. But that created a hidden structural weakness no one caught. Until it was too late. Let me take you through exactly what happened. From the original design, to the shortcut that was taken, to the moment everything collapsed. It starts in 1964. The Minnesota Department of Transportation needs a new bridge to connect downtown Minneapolis with the north side of the city, across the Mississippi River. They hire a civil engineering firm. The design is a steel truss bridge, 8 lanes wide, 1,900 feet long. Steel truss bridges are common, strong, efficient. The weight is distributed through a network of triangular supports. Forces are spread across multiple members. If one member weakens, the others can compensate. That's the theory. The original design called for thick gusset plates. Gusset plates are the metal connector pieces that join the truss members together. They're bolted or welded at key points. They're critical because every load, every car, every truck, every ton of concrete passes through these plates. The engineers calculated the required thickness based on the expected loads, traffic weight, snow, wind. They specified 1-inch thick gusset plates at critical connection points. But during the design review, someone raised a concern. Cost 1-inch plates are heavy, expensive, difficult to fabricate. A project manager suggested a change. Use half-inch plates instead. Half the thickness, half the weight, easier to handle, cheaper to produce. The question went to the design engineer. He ran the calculations. Half-inch plates would work, technically, if the load stayed within the original assumptions, if traffic didn't increase significantly, if maintenance was rigorous. He approved the change. The project moved forward. The bridge was built with half-inch gusset plates. Construction finished in 1967. The bridge opened, and for 40 years, it stood. This is where the hidden risk entered. Because those thinner gusset plates had less margin for error, less capacity to handle unexpected loads, less ability to tolerate stress concentration. And over time, the loads on the bridge increased. In 1967, average vehicle weight was lower. Fewer trucks, smaller cars. But by 2007, traffic volume had tripled. Trucks were heavier. SUVs replaced sedans. The bridge was carrying far more weight than originally designed for. And there was another factor: maintenance. Over the years, the bridge surface was resurfaced multiple times. Layers of asphalt and concrete were added. Each layer added weight. By 2007, there was an additional 2 inches of concrete across the entire deck. That's an extra 20% dead load. Permanent weight. The structure had to support 24/7. Engineers warned about this. In 1990, a routine inspection flagged several gusset plates showing signs of stress, bowing, slight deformation. Not critical yet, but concerning. The report recommended monitoring, but no action was required. The bridge was still considered safe, within acceptable tolerances. In 2001, another inspection, the same gusset plates were flagged again, this time with more visible deformation. The inspector noted, gusset plates at connection U10 show significant bowing under load. Recommend detailed analysis. A detailed analysis was scheduled, but funding was tight. Other bridges had more urgent needs. The analysis was delayed, then delayed again. By 2007, it still hadn't been done. On the day of the collapse, there was additional load on the bridge. Construction equipment, gravel, concrete. A resurfacing project was underway. 4 piles of construction materials, each weighing several tons, concentrated on the center span, right above the weakest gusset plates. At 6:05 p.m., one of those gusset plates failed. The one at connection point, U10, the same one flagged in inspections. The half-inch plate that had been carrying loads for 40 years finally couldn't handle the stress anymore. When it failed, the load shifted to adjacent gusset plates. But those plates were also undersized. They weren't designed to handle the redistributed load. Within seconds, they failed too. This single parameter changed everything. Because in a truss bridge, the failure of one connection point creates a cascade. The forces don't just disappear. They transfer, amplify, overload the next weak point. The center span dropped first, then the approach spans, one after another. Like dominoes, the entire bridge collapsed in less than 30 seconds. The investigation took 18 months. The National Transportation Safety Board analyzed every piece, every calculation, every decision. Their findings were clear. The gusset plates were undersized by about 50%. They were never thick enough to handle the loads they were subjected to, especially after traffic volume increased and deck weight was added. The design change from 1-inch to half-inch plates was the root cause. It created a hidden structural vulnerability, one that wasn't caught during inspections. Because the plates looked fine from the outside, the deformation was subtle, and the inspection protocols didn't include stress testing of gusset plates. What should have been done differently? First, the design change should have triggered a full reanalysis, not just a quick check, a comprehensive evaluation of how the thinner plates would perform under real-world conditions, including future traffic growth, including potential deck resurfacing, including worst-case scenarios. That analysis would have revealed the inadequacy, and the plates would have been made thicker, or the design would have been adjusted to reduce stress concentration. Second, the inspection findings should have been acted on when gusset plates showed deformation in 1990 and 2001. That was a warning sign, not a guarantee of failure, but a clear indication that the structure was being stressed beyond original assumptions. A detailed analysis should have been completed immediately, not delayed for budget reasons, not postponed for years, because infrastructure doesn't wait. Stress accumulates, fatigue grows, and eventually, something gives. Third, load limits should have been enforced. When it became clear that the bridge was carrying more weight than designed for, additional resurfacing should have been stopped, or traffic restrictions should have been imposed, or structural reinforcement should have been added. But none of that happened, because the bridge was still considered safe, because no one expected a catastrophic failure, because the risk was invisible. Here's a question. If you were the project manager in 1964, and you were told that switching to thinner gusset plates would save $200,000, would you approve it, knowing that it met minimum code requirements, knowing that it would pass inspection, knowing that the bridge would likely stand for decades? Most people would say yes, because it's a rational decision. It meets standards, it saves money, and the risk seems theoretical. But that's the lesson. Engineering isn't about meeting minimums. It's about anticipating what happens when conditions change, when loads increase, when maintenance is delayed, when the unexpected happens. The I-35W bridge didn't fail because of a single mistake. It failed because of a chain of decisions, a cost-saving shortcut, delayed inspections, increased loads, and a system that assumed everything would stay the same. But nothing stays the same. Traffic grows, materials age, conditions change, and the margins that seemed safe 40 years ago become inadequate. The bridge collapse killed 13 people, injured 145, cost over $400 million in damages and replacement, and it revealed a national problem. Hundreds of bridges across the United States were built with similar design shortcuts, similar thin gusset plates, similar hidden vulnerabilities. After 2007, inspection protocols were updated. Gusset plates became a priority. Load limits were reassessed, and many bridges were reinforced or replaced. But it took a catastrophe to make that happen. It took 13 deaths. It took a bridge collapsing into a river during rush hour. That's the cost of ignoring critical limits. The cost of assuming that because something has worked for 40 years, it will work forever. The cost of prioritizing budget over safety margins. If you work in engineering, infrastructure, or any field where decisions affect safety. Remember this: the shortcuts you take today might work for years, for decades. But eventually, conditions will change, and the margins you cut will matter. Design for the worst case, not the expected case. Inspect rigorously, act on warnings, and never assume that because something hasn't failed yet, it never will. Because bridges don't collapse because they're old. They collapse because the risks were always there, hidden, accumulating, waiting for the moment when everything aligns. And when that moment comes, there's no second chance. If this video made you think differently about engineering decisions, subscribe, because there are more stories like this. More failures, more lessons, more critical limits that were crossed. Until next time, respect the margins, question the shortcuts, and never forget, what seems safe today might not be safe tomorrow.